Now let's see what is the performance of the paging. So the performance means if we have the direct access, so direct access main memory time is M, let's say M nanosecond or M millisecond. So we consider that this is the time for accessing the main memory. And if we are using the paging, then what will be the access time? So we know that first what will happen is CPU generates the logical address, and this logical address is of two part in the paging. One is the page number, another is the page offset. This will concern to the page table, and it will find out a particular frame from that particular page table. So from the page, it will find out the frame, and this particular frame will be given to another part, that is the frame number and the frame offset, that is the physical address. We are converting it, and from the physical address we are going to the main memory and getting that particular word that we are looking for. So let's assume that this is your main memory or physical memory. So this is how it will be done. We assume that the translation of the physical address to the from logical address to the physical address, it is taking, let's say, m time. And to access the data, as we know that main memory access time is m. So what is the memory access time here in this particular case? That is called effective main memory access time, or effective memory access time, or it is also called average memory access time, which will be calculated as 2m. How 2m is coming? M, this one is M for translation of the logical address to physical address, plus M, which is for main memory access, or you can say the data access. So this is how the time will be taken by the paging, right? So previously it was M, now it is 2M. So the time has been increased. And for accessing it, we have to convert the logical address to physical address using the page table access time. It is taking time. And again, we are getting the main memory, the word from the main memory or the byte from the main memory. It is also taking m amount of time. Do we have any technique which will further reduce this 2m to some amount? Do we have some technique? So yes, we have the technique, that is called paging with translation look aside buffer. So we'll use another hardware here. This particular hardware will be used in between these translations, and we use the concept of locality of reference. So what is a locality of reference? It says that if we are executing a particular process, so we know that what instruction will be the next instruction, or what byte will be the next byte. So all the next byte of the current process we are putting into the buffer that we'll use here. So this is how it looked like. So another hardware has been used here, that is called TLB, translation look aside buffer. That will act as a cache memory or a type of cache memory. So translation look aside buffer is a faster access memory like cache memory. And here what we do is we put those pages or those instruction which will be which is going to use in future using the look aside using the locality of reference concept. So in between the page table and the logical address generated, we have the TLB here. I'll let you know that what is the significance of this particular TLB here. Now, you just see what is TLB. So it is a special hardware which holds the entry of the current running process, current running. So here we have a small entry of the only process which is running right now. So it will take all those pages entry related to the process which is currently running, and its context switching entry become invalid. So whenever we are doing a context switching means when the process will be changed from in the CPU. So let's say in the CPU, uh, right now it is process P1 is running right now, and let's say P1 is going out and P2 is coming. So that particular process is called context switching. So whenever we have the context switching, all these entry will be invalid, and we have to put all those again those pages which is currently running on it. So that is the translation look aside buffer. Okay. Now, what is the concept here is, so when we have the logical address and it is generated by the CPU, we'll see the page number here in the TLB, because TLB is a cache hardware, or you can say the special hardware which is attached in the CPU itself. It is much faster than entry into the page table, because page table entry is in the main memory. So here you can see the TLB is there in the cache memory. So to access that, it is taking a very less amount of time. Whenever there is if there is a entry, so it is called TLB hit, means if you find out that particular page in the TLB register or this TLB table, we say it is a hit. If that page is not there, then there is a miss. So what we have to do, we have to go to the page table, because in the page table we have the entry related to a particular process. So again, or particular program or particular process which is running right now. So this page table has the entry of a particular process. So for the particular process, we can go here, and here we have, will go when there is a miss. So you can see here we have, let's assume that to access this particular TLB, it is taking T amount of time, and physical access of the memory, it is taking, let's say, M amount of time. So we are assuming that this T is very less than M. Getting it? Because page table is also in the main memory. So here also it is taking an amount of time, and then it is getting the frame number from that. It will take the frame number and convert the logical address into the physical address. Again, M amount will be taken. So when there is a hit, it will take T plus M time. And when there is a miss, it will take how much time? So T plus M plus M, it means T plus 2M. So you see, if there is a TLB hit, so in the TLB hit, what is the effective memory access time? So effective memory access time will be T plus M, right? And if there is a TLB miss, so what is the effective address memory address time, or you can say average memory address time? It will be how much? So T for searching here, plus M going here, and plus M going here. So it will be T plus 2M. And what we are looking for? We are looking for the possibility which will reduce the time from 2M. I need the time which is less than 2M. But here, if there is a miss, it will be more than 2M, right? And if there is a hit, it will be less than TM. Why? Because we assume that T is very less than M. Otherwise, it is of no use, right? So why it is T is very less? Because it is the cache cache memory, and cache memory is, you can say, it is a type of register which is inside the CPU, so it is taking very less time. Now assume something. Let's assume that how we can calculate the with the hit as well as with the miss. So we assume that the effective memory access time or average memory access time with this TLB will be equal to what? Hit. That is a, if there is a hit, then we are taking how much time? We are taking T plus M time. Plus, if there is a miss means 1 minus hit, then we are taking T plus 2M time. And what is this hit? Hit is nothing but hit ratio. Hit ratio. Hit ratio means how many time we have reference, how many time we got it, and divided by how many time we have reference. Means how many time we got the page divided by number of time we got the page and number of time we have done the page reference. So let's say if 9 time I am getting the page out of 10, so it will be how much? Hit ratio is 90%, right? Or you can say 0.9. So if we'll assume that the hit ratio is, if you'll assume that his hit ratio is 90%, so what is the effective memory access time? It will, in TLB, it will be calculated as 0.9 of T plus M. So let's assume that, let's assume all the parameter. Let's assume the parameter as, if let's say M equal to 100 nanosecond, so I think you got this particular equation, right? How we can get the hit. So number of time we got divided by number of time we have referenced that particular page. So number of time we got that particular page and number of time we reference it. So let's talk about one problem. So let's say we have M means how much time we are taking from physical addressing is M, right? How much time we are addressing this physical memory. So let's assume that this is T, this is M, and this is M. This is T, okay? So M we are getting as how much? 100 nanosecond. Hit ratio we are getting as 90%. T value, that is the time taken to access the TLB, translation leukocyte buffer, is let's say 20 nanosecond. So what is the average effective memory access time? So that we have to calculate. So what is effective memory access time with TLB, paging with TLB, will be 0.9 of T plus M. What is T? T is 20 plus M. M is 100. It will be 120, right? 100 plus 20, it will be 120. Plus 1 minus it will be 0.1 into T. What is T? Is 20 plus 2M. 2M means 200. 200 plus 20, it will be 220. Now, if we are making a 120, 90% of 120, it will be 108 plus 10% of 220, it will be 22. So total it will be 130 nanosecond if the hit ratio is 90%. So you can see the TLB is performance of the TLB is totally depend upon the hit ratio of the TLB. If in the TLB there is a miss, we have to give the penalty. So if you'll assume that the same thing will happen and you assume that the hit ratio is right now, everything is same, but hit ratio is, let's say, 10%, then what will happen? If hit ratio will be 10%, then this effective memory access time will be calculated as 0.1% of 120 plus 0.9% of 220. So I think you got the uh, you got the got the condition here, because if we calculate like this, it will become 198 plus 10% of 120 will be 12, and the total will be 210 nanosecond, which is more than 2m, which is more than 2m. 2m will be how much? 200, and it is more than 2m. If the hit ratio is very less, if the ratio is very high, then you can see this is 200, right? In the normal paging is 200 nanosecond. But if you are using TLB with 90%, we are getting 130 nanosecond, and TLB with hit ratio as 10%, we are getting 210. So you can see these are the differences. So TLB is totally depend upon the hit ratio. Hit ratio we have to see in the TLB, and we have to put those pages which going to be used in the future as the concept of locality of reference, right? So with this, you got the idea about paging with TLB, that is translation look aside buffer.